All right, and next what we want to do is we want to look at capacitors. All right, so we're going to look at capacitors. The basic idea about a capacitor is capacitors store energy. Did you see that? The hall light just came on. In the form of charge for later use. So in a way, they're like flywheels for electric circuits. All right, so if you want to store up some charge and use it later, you can use a capacitor to do that. Just like if you want to take some energy and store it up, you can store it up in a flywheel, keep it rotating. And then when you need it later on, you can use friction to take that energy out of the flywheel and put it into some other object. Right? So that way you can do the same sort of thing in a mechanical system. So this is the electric version of the flywheel, a capacitor. There's some very interesting things. The basic idea about that is the charge that is stored, Q, is going to be equal to the capacitance, which is a property of the capacitor, and that's just something you have to build up, times the difference in the potential on either side of the capacitor. So capacitor looks a little bit like a battery, right? The only difference, I mean, it's two parallel lines. It doesn't have a short and a long side. They're both the same size. So that's the basic way you can tell. It's better to draw the battery with the short one a little fatter so that I can tell that it's a battery, because if you draw them real quick, sometimes you can't tell. I mean, that's the way it is. So if on one side you have a voltage V0 and on the other side you have V0 plus delta V, this is going to come from your battery. We'll see that next time. Then you have Q over C as the voltage drop. That's going to be equal to delta V. That's just what this says. So that's the amount of charge you're going to store up on one plate. So this guy's going to be minus Q, this guy's going to be Q. The simplest way to look at this is a parallel plate capacitor, which is just two parallel plates. The ones that you actually use in a circuit are usually rolled up capacitors. Right, so there's a bit of a difference there. That gives you a lot more capacitance in a smaller area. Parallel plates are not a really efficient way to make a capacitor. They are, however, easy to make in a lab and do experiments with if you want to do those kinds of experiments with undergraduates. So this is the charge on one plate. Now this is the absolute value of the charge on one plate. Because one plate is going to have a positive charge, one plate is going to have a negative charge. This is the capacitance, which is a value, a value for the particular capacitor that you're using, so you're going to look that up. It's going to be in picofarads or microfarads. They don't do nanofarads, they just do micro and picofarads. And this is your EMF or your potential difference. Okay, and we want to look at these in series and parallel. In series, you store less charge. So remember, series is something like this. You have one element, a break, and another element. Okay, and if this one has C1 and this is C2, right? If you look these up, if you just pull these out of a package, this one may be 10 microfarads, this 5 microfarads, something like that. You put them in series, and we'll have some effective capacitance for that. That is going to be given by 1 over c is equal to 1 over c1 plus 1 over c2. This may remind you a lot of springs, right? That's exactly what we had for springs in series. So this is how you calculate with two things in parallel what the effective capacitance is, right? And that's because basically you've got things farther away, right? Because you have them farther away in a sense. If you had two parallel plate capacitors, it would technically be farther away, but if you have this, you just have the sort of idea farther away for more complicated capacitors that are made either electrolytically or by rolling them up or something like that. You basically have the plates farther away because you have a gap here and a gap there. So that means the difference between the negative and the positive terminals is larger, the physical difference. And so the physical difference is larger. With the same voltage, you get less capacitance. Okay, that's the rule. Part B is going to be in parallel. And strangely enough, that's going to give you more charge. More capacitance. So in parallel, remember we had something like this. How close am I at the bottom? There it is. Now in this case, they no longer have to be the same. They only have to be the same in the wires, the same capacitance in the wires because, or in the battery case, because these two guys had the, in the battery, there'd be a current flow. Here there's no current flow from one to the other. Or there is technically, but but that balance out gives us this next equation. The way that balances out is going to be, you just add them together, C1 plus C2. So the capacitance of the two things in parallel is the sum of the two capacitances, which basically is like having extra area. So you have the area for the same plate in a way. So you have larger area, you can store more charge. If you had a larger plate, you could store more charge. And that's what this tells you here, only with two different objects. So it'd be like having, instead of doubling the size of your plate, it's like having two plates side by side. Right? That would be your capacitor. Probably should have drawn that in there because now it's all messy. So the last thing is I told you that we had to deal with energy. And that is proportional to delta V squared. That is the energy of a capacitor. This is how much energy it stores. The energy it's storing is going to be equal to 1/2 the capacitance times the voltage over this squared. And that's going to be equal to 1/2 Q delta V, right? The charge times the potential. So these are really the same thing. All I've done here is I've taken this formula and plugged it in there, right? This is how much energy it's storing up. So if you have a higher capacitance, you store more energy linearly. And if you have a higher voltage, you store more energy quadratically, right? If you double the voltage, if you had, instead of having one battery, right, like that, you had two batteries like that, and then you had your capacitor. What you do is you start storing twice as much charge, but that twice as much charge would become 4 times as much energy. All right, so that's pretty useful, right? So higher voltage, means much more energy as you increase that voltage, which could be good, could be bad. For us, it's neutral, right? For us, it's neutral. It's just a fact. But if you're actually designing things, that could be very important, right? If you feel like designing anything. Again, the problem for this, like I said last time, will be taking a couple of capacitors in parallel and putting another one in series and finding the equivalent resistance or equivalent capacitance. And that will hopefully give you some ideas about how you proceed with these kinds of problems. All right? Bye now.